Hello, am I audible?
Yes.
Good evening, everyone. The 19th episode of bi-weekly webinar series of Malabar Subsection is hosted by Government Engineering College, Kozhikode. I am thrilled to welcome you all to the webinar today on Introduction to Machine Learning Algorithms. My name is Navya and I will be the host for this session. Before beginning the session, let me introduce our speaker, Dr. Shaji Mohan BS, Professor and Dean Research, Government Engineering College, Kozhikode. He has been working in various premier engineering institutions in Kerala since 1991. He took his PhD from Computer Science and Engineering Department, IIT Madras. He had presented papers in many national and international conferences in India and abroad. He won the Best Paper Award in International Conference on Advanced Computing and Communication in 2006 and in the International Conference on Intelligent Systems and Image Processing 2014, Nippon Institute of Technology, Japan. He received the Best Paper of the Year 2015 award at International Journal of Industrial and Instrumentation Engineers, Japan. He is a life member of Indian Society for Technical Education. His research interests are machine learning, kernel methods, pattern analysis, speech processing, data networks, and data compression algorithm. Sir, I humbly welcome you to this session. Last but not the least, on behalf of Malabar Subsection and IEEE GEC Kozhikode, I welcome each and every one of you present here to the 19th bi-weekly webinar series. During this session, we encourage you to participate actively and engage with our speaker by asking questions and sharing your thoughts in the chat box. We want this to be an interactive session where we can learn from each other and exchange ideas. So, without much delay, I humbly welcome Dr. Shaji Mohan sir to handle the session. So, please.
Okay. Once again, a very good evening to all of you. Let me start my talk without much delay. The topic of discussion today will be the introduction to machine learning algorithms. I will just show an outline of what I'm going to do today. This is the outline of my presentation. So the outline is discussing types of machine learning techniques. So we will be discussing what are the basic techniques or the primary techniques or methods that are used for learning purpose. What are the different learning strategies? So we will discuss a little bit about supervised learning techniques, unsupervised learning techniques, and also learning technique, which is also known as the reinforcement learning. We'll also discuss some basics of that. Of course, there are many other different types of learning techniques, such as semi-supervised learning and so on. But these are the popular techniques that have been used in machine learning. After that, what we are going to discuss are popular machine learning algorithms, because if you want to approach a machine learning problem, or if you want to do some machine learning or something like a pattern analysis or a machine learning task, we should know what type of algorithm we have to select for a particular task. We know that machine learning basically deals with the classification, regression, clustering sort of things and all. So for each and every type of these techniques, we may have to use certain algorithms. So some popular algorithms, this is only a few algorithms which are very popular, and we'll discuss some basics about the linear regression, support vector machine algorithms, naive Bayes algorithm, k-nearest neighbor algorithm, k-means algorithm, principal component analysis, and finally we will conclude. So these are the overview of my presentations. Straight away, most of the contents in these presentations are adapted from the internet sources. So with this forward, I'm just going into some basic history of machine learning, because we know that machine learning is actually one of the offspring of this artificial intelligence. So basically, artificial intelligence, generally people started talking about artificial intelligence somewhere in 1940s onwards, and somewhere in late 1970s or 80s and all, the initial discussions on machine learning came into existence, and nowadays in 2020 or 2023 and all, people are discussing about the features and the possibilities of deep learning, where you are using layers of learning networks and all those things. So it is getting very prominent in today's scenario. So this is an evolution of artificial intelligence, machine learning, and deep learning. So basically, machine learning is a branch of artificial intelligence, or basically it is a subdomain of artificial intelligence. This intelligence is actually, it is something which is being acquired by actually what artificial intelligence is. Intelligence is the property, or it is the capability of a human being. Human being can acquire intelligence from knowledge or information or simply data. When they acquire data, data is refined into something like a knowledge and or information. When you again refine information, it will come to the knowledge. And once again, you refine knowledge, it will become intelligence. So human being gather or acquire intelligence all over from the environment, whatever the things he learns or he collect from the environment or he learns from the environment, intelligence is being built. Some sort of a data, some sort of a knowledge base, and from that knowledge base, certain intelligence is being built. Now, what we want is we want to incorporate that intelligence into machines. So, or artificially, we want to incorporate intelligence into machines. That is basically known as the artificial intelligence. And machine learning is a branch of artificial intelligence that enables the computers to learn themselves or self-learn. Computers can learn by themselves from the training data, because they can learn from the data which they acquire, and that data we'll call it as the training data. And these training data can improve over the time and without being explicitly programmed. Basically, the systems or computer systems that can behave in two different ways. One is a programmed way, and the other one is a learning-based way. So computers generally used as a programmable device, but when you incorporate the learning capability, they can take decision by themselves, or they can learn from the data or the training data, and based on that learning, they can again acquire intelligence, and they can take and they can make some steps, or they can take some initiative, or they can take or do some activity based on the intelligence they have acquired from the training data. So in order to provide that capability, we need artificial intelligence. And machine learning is the certain group of algorithms and techniques altogether, which will be basically making use of the possibility of artificial intelligence. Machine learning algorithms are able to detect patterns in the data and learn from them. So basically, there are underlying patterns in the data, and using machine learning techniques, we can acquire what is the underlying patterns, and based on that, we can understand what is really in the data, and based on that, we can acquire knowledge, we can acquire intelligence, we can acquire information. All these things we can acquire from these patterns, and based on the intelligence we acquired, we can take decisions in future. So that will help you in making certain decisions. So that is what is basically artificial intelligence, machine learning. And the last thing is the deep learning. Deep learning is actually making use of different deeper layers of neurons or deeper layers of intelligent neurons to further refine details and to have a better representation and make a better decision based on the refinement of the data and using layered architecture and all. So that is what is known as a deep learning. Deep learning is nowadays getting a lot of prominence. We'll go to the next slide. This is basically illustrate the human being, the intelligence which are being, I can learn everything automatically from experience. So basically learning is the property, or learning is the capability being exhibited by human being. Human being can learn. Learning is the capability, or learning is, we have the capacity of learning. How we learn? We can learn from the environment, we can learn from our parents, we can learn from the books, we can learn from the different resources, we can learn from classroom teaching, we can learn from books, we can learn from internet resources, we can learn from the experience. Like that, as a human being, in a lifelong way, the human being learns, and basically based on the learning, he acquires a lot of knowledge. And this knowledge will act as a knowledge base, and from the knowledge, intelligence can be extracted. Intelligence are more refined forms of knowledge, and based on this intelligence, human being normally takes certain decisions. Say it will help you to operate a machine. When you are learning about the skills of operating a machine, it is you are learned that skill, and when you acquire that skill, you can operate a machine. So what human being want, or scientists want all these days, is as human being can learn from all these ways, why can't we do the same thing for a machine? So if you, and whether it is possible or not, that is given rise to artificial intelligence, machine learning, and further into deep learning and all those things. Here the machines, or the machine or robot or the computer system says that, yes, I can also learn from the past data with the help of machine learning. So machine learning is the way in which you can make the systems or computer systems or mechanical systems can learn, the computers can learn, so that further they can take decisions based on the knowledge they have acquired. So this is an overall introduction about the machine learning. I hope you understand. Okay. We'll come to our topic, Introduction to Machine Learning Algorithms. Machine learning algorithms are the programs that can learn from the hidden patterns from the data. So training data, or what we call it as training data, contains certain hidden patterns. And once you can understand the hidden patterns, you can predict what can be from this data. You can predict some certain outputs or certain things what you need to have, and improve the performance from the experiences of their own. Different algorithms can be used in machine learning for different tasks, such as simple linear regression that can be used for predictions. Regression is a type of machine learning problems. Classification is another type of problems. The basic difference between a classification task and a regression task is classification, you are assigning a class label to an unknown entity. Normally, a classifier, building a classifier is you will be building a model by using the training data. You will have the training data. Using this training data, you will train a network or you will train a system and build a model for classification. Once you are happy or satisfied with the training process, you will stop the training and then the model is ready. You can use this trained model for an unseen example XT, and you can label that XT. Say for example, suppose you train a model with a lot of say human faces like African faces, Chinese faces, Asian faces, and the model has been trained. That means the model has been trained and now it is capable of doing a classification task. Later, you supply the model or input the model with some human face, which may be an African face or an Asian face, and use basically making use of the learned capabilities. It will predict that this particular face is an African face or a black face or an Asian face or a Hispanic face. This is basically used in classification tasks. Classification is essentially a machine learning task which is more popularly used in many different areas. And the basic operations which are happening in the classification task is an input. The model is being trained with a lot of training samples. The model is built. Once the model is built, you can use it for assigning the class label of an unknown entity. This is what is a classification. Classification is a prominent problem in a machine learning. Another prominent problem in a machine learning is the regression. Regression is simply, we can say it is a function approximation. Regression can be linear regression or polynomial regression. Basically, the output of the regression is a continuous variable or some value. Say, for example, what will be the weight of a person when he is around 56 years of age? Suppose you have the previous historical data. When the person was around 10 years, his weight was like this. When the person was 12 years old, his weight is like this. When the person is 20 years of old, age, his weight is so and so. From this, you can have a prediction. What will be the age of that person when he turns out to be 80 years of age? So the model will predict that at the time of 80 years of age, or when he is becoming 80 years old, his weight will be some 46 kg, something like that. That 46 kg is the output which is available at the output of the regression model. So that is basically the difference between regression and classification. Basically, classification means assigning a class label to an unknown entity, or you are classifying an unknown entity. And regression means you are predicting function approximation, or you are predicting what will be the value of that function at that particular value of the x, what will be y. So that is basically the regression and classification. Now we'll come to different types of machine learning algorithms. Machine learning algorithm can be broadly classified into supervised algorithms. Say here it is supervised algorithms. Then we have unsupervised algorithms, unsupervised learning algorithms, and we have reinforcement learning. We primarily discuss this. Of course, we are having different other different types of learning algorithms like semi-supervised and all. In the case of supervised algorithms, and generally the below diagram illustrate the different machine learning. Actually, these are not the complete set of algorithms. We have supervised algorithms here, and we have unsupervised here, and we have reinforcement. Under the supervised algorithm, we have regression. Under the regression, we have polynomial regression, linear regression, polynomial regression, linear regression. We have decision tree algorithms, random forest algorithms. We have a broad category of classification algorithm. Classification, of course, we have discussed. We have a broad area of classification algorithms, something like k-nearest neighbor algorithm. We have a truss algorithm, logistic regression is there, naive-based classifier is there, support vector, like that. The list extends like these are all these ways. Unsupervised examples of unsupervised learning techniques are clustering is one most important application of unsupervised, or it is basically the clustering techniques, singular value decomposition, principal component analysis, k-means clustering, And these are all different types of clustering algorithms. And we have also association analysis like a priori algorithm and a frequent pattern growth algorithm, hidden Markov algorithm model. These are all different categories which are categorized as unsupervised algorithms. Reinforcement, we have continuous and categorical type of reinforcement algorithm. We'll just go through each and everything, just to have the idea what and all these things do. So basically coming to the supervised algorithms, I hope that screen is visible. Supervised algorithm, as the name indicates, that learning technique, the supervised learning technique basically needs a supervisor. Who is a supervisor? In a classroom of students, the supervisor is a teacher. For doing a research work, you will be having a supervisor. Supervisor means he knows everything, or he is the guide, or he is something guiding, that he is offering the guiding principles or something like that. But in the case of a pattern analysis, the supervised information is something like labeled example or the ground truth, or we have sufficient number of labeled examples. And using this labeled information, suppose you have thousands of examples, say for African faces, thousands of examples for American faces, thousands of examples for Chinese faces. All these are actually labeled examples. So these labeling or these labels act as the supervisor. Supervised learning is a type of machine learning in which the machine needs external supervision to learn. So basically the supervision is provided by the label. The supervised learning models are trained using the labeled data set. So for supervised learning, you need a huge amount of a data set which contains a lot of labeled examples. These labels are actually the supervised information. Once the training and the processings are done, the model is tested by providing the sample set or sample test data to check whether the prediction is correct or not. So basically, the entire data set we'll categorize into training data set. Something like an 80% of the data will be taken as a training, which is already which already have the labels, and the remaining 20% we know the label, but for the time being we'll just make sure that this label information is not given. It is given as a test, and we will test it. The goal of supervised learning is to map the input data with an output data. Output data is the label, input data is some features or some feature vector we are giving to the model. Supervised learning is based on supervision, and it is the same as when student learns things in the teacher's supervision. It is just like our fundamental or classical classroom method of teaching, where the teacher explains, the student learns. When the model is being built, the supervised information, something like labels, actually with the labeled examples, we train the model. So that is why it is known as a supervised. The most popular categories or most popular applications of supervised methods are classification and regression, which already we have discussed. Classification means labeling. We are assigning a class label to an unknown example. Regression is basically function approximation, where we are predicting what will be the value of the function or fitting a function to the data. Examples of some popular supervised learning algorithms are regression, decision tree, logistic regression, k-nearest algorithm, support vector machine. All these algorithms, popular algorithms, belong to supervised learning algorithm. Now we'll come to unsupervised learning algorithm. As we know that in unsupervised learning technique, the labeled data is basically very sparse or basically nil. We don't have any labeled information. That means data is not having any label. It is a type of machine learning in which the machine does not need any external supervision to learn from the data, hence called unsupervised learning. The unsupervised models can be trained using unlabeled data. Unlabeled data set means as basically the training is generally done using unlabeled data set. You can see that unlabeled data set, and that is not even being a label, that is not even classified or nor categorized, and the algorithm needs to act on that data without any supervision. In unsupervised learning, the model doesn't have a predefined output, and it tries to find useful insight from the huge amount of data. Basically, it is getting the insight from the data which is given to the model. These are used to solve the association or clustering problems. The most popular techniques, which is basically belonging to the unsupervised algorithm, is the clustering. We'll discuss the k-means clustering later, and we'll find out how without the labels you can categorize or you can cluster a huge collection of the data into different clusters. So we don't even need the labels, but only information we require is actually how many types of examples are there in the total data set. If you know that particular k value, then we can cluster it. So basically clustering is a very good example of unsupervised. So now we know what is supervised, we know what is unsupervised. Actually, there is something in between is also there, which is known as semi-supervised learning, which is actually a method where the labeled information is actually very, very less. We have the access to the labeled information is very, very, that is, we have a very few examples that are being labeled, but most of the training examples are not having labels. So first thing you have to do is how to get the unlabeled examples in the training set labeled. And once all the training examples are labeled, then we will do the actual classification of clustering tasks. So association algorithms, all these techniques are being examples of unsupervised. Now, one popular method of learning is the learning process is reinforcement learning. In the reinforcement learning, there are two basic things. One is basically there is an agent. There is an agent and there is an environment. So agent and basically agent is actually interacting with the environment. So reinforcement learning, an agent interacts with the environment by producing actions. So the agent produces some actions and learn with the help of a feedback. So from the environment, he may get the feedback. So basically, there are two different types of feedbacks are possible. One is basically known as the rewards, and another one is punishment. Something like, suppose you do some sort of actions, punishment, that is punishment or reward. So punishment, as we know, it is something like a negative way, and reward means you are appreciated or you are getting encouragement. So basically, the feedback is given to the agent in the form of rewards or in the form of punishment also, such as for each good action, he gets some positive reward. And for each bad action, he gets a punishment or a negative reward. This negative reward is known as the punishment. There is no supervision. Basically, this is very close to the unsupervised thing. There is no labeled example, nothing. Where the agent interacts with the environment, he provided some actions to the environment, or he provides some actions. Based on the actions, he may get rewards or punishment. And based on that, he may refine his actions. He may modify the actions. Like that, he may land into the goal. This is basically an overall idea about reinforcement learning. Generally, reinforcement learnings are very much useful in game playing. Most of the social network analysis, social media, social network, and all sort of analysis, game playing, gaming, in all the different areas, this reinforcement learning is getting very good applications. So basically, it has got an agent. Agent will interact with the environment. Agent will produce some actions, and the actions will be rewarded or punished. Based on the rewards or punishment, the agent can modify his actions, and finally, it may go towards the goal. This is basically the idea behind reinforcement learning. Okay, now we'll go to this slide will show you how this reinforcement learning. So the raw input data is there. You can see that the raw enforcement data basically contains three different types of entities. It contains some square. There are some pink stars. There are blue stars. So basically, the total data contains three different entities or three different categories. And basically, this may be a classification task. And the agent basically interact with the environment. There are some awards, and there is a reward. There are some punishment, and the agent will keep on producing some actions and start switching from one state to the other. Finally, he may reach the goal state based on the inputs, the feedback he is receiving. The feedback can be either rewards or it can be even punishment. And at the end of the day, when the algorithm terminates or reaches the goal, you can see there are 5 sets of information. That is basically the input data. The all items are separated like this. You are getting 3 distinct sets, or the things are basically classy or categorized or clustered into 3 sets. So this is basically an example of how a mixed data which contain 3 different classes or clusters are categorized. The agent will try to modify the data, separate the data based on certain algorithms or something like that. He may get reward or he may get punishment. Based on that, every action he may just transit from one state to the another state. Finally, he may reach the goal state. At the time of reaching the goal state, he will be at the end of the day, when the agent reaches the goal state, we have 3 distinct sets. This is basically a classical clustering task, which is being done with the help of the reinforcement learning. So I hope you understood the basics of the reinforcement learning. So now we will switch over to popular learning algorithms. I will list some 10 popular learning algorithms, but we will not be having time to deal with all the learning algorithms. So we have linear regression, we have logistic regression, decision tree algorithms, support vector machine algorithm, naive-Bayes algorithms, or different Bayesian algorithms or Bayesian classifiers, k-nearest neighbor algorithm, K means clustering algorithm, random forest, a priori algorithm, principal component algorithm, like that. So many are. There are hundreds of machine learning algorithms are there, but we will discuss certain possible very popular algorithms. The first thing we are going to discuss is the linear regression. Linear regression, actually there is a linear regression and we can also have polynomial regression also. Regression methods fall under the category of supervised machine learning. So generally we know that we have three fundamental categories of the learning techniques, that is supervised, unsupervised, and reinforcement, of course. And regression generally belong to the supervised learning strategy. They help to predict or interpret a particular numerical value based on the prior data. This is not a classification. Basically, it is the function approximation. That is when the function basically predicts a particular output value. So the numerical value, basically the output will be a numerical value. Such as the asset of the price based on the past pricing data, or for similar properties, or something like what will be the age of a person, what is the weight of a person when he reaches the age of a particular age, or what is the value of the function when x is like this, what is y, something like that. The simplest method is linear regression. Linear regression is the most simple way of explaining regression, where we use mathematical equation. Like linear regression is basically approximating, we are approximating the data distribution as a line. So suppose you have a certain data distribution, something like that. So we may predict that the function is as, or we may fit a line. So basically we know that the line, the expression is y is equal to mx plus c, where c is the y-intercept. Suppose you have the y-intercept and all those things. This is the y-axis and this is the x-axis. Y is equal to mx plus c, where m is the slope and x is the continuous variable or input variable. Y is the output variable and c is the y-intercept. So basically, if you want to predict, or if you want to fit the data examples to a line, what you require is you want to find out what is the value of the what is the value of the slope and what is the value of the y-intercept c. So that is what is given here. The simplest method is linear regression, where we use the mathematical equation y is equal to mx plus c or mx plus b, where our model to the model data set. So the entire data set is actually modeled as a line. And whenever the data training point is away from the line, that much error is there in the prediction. That is there. So with multiple data pairs, and by computing the position and slope of the line, and that minimizes the total distance between the data points. So basically what you are finding is you are finding out the most suitable line where the individual distance, or basically this distance from the line to an actual data point, that is from all the data points, is minimized. So basically you are trying to find out a line that basically represents the entire data distribution. So in that case, the line is being obtained by considering or an optimization problem that minimizes the distance between each data point. That aggregation of the distance or the difference between each data point from the line is minimized. So like that, we are finding out a line. This is what is known as a linear regression. And you will be finding out the optimum value of m, and you will be finding out the optimum value of c. That means the optimization problem at the end of the day will give you what is the optimum value of the slope, what is the optimum value of this y-intercept. That means you just fit a function, that is a line, to this data set, so that at any point, if you just have any x, you can find out what is the value of y, what is the value of the function. So this is basically a very interesting problem, which is called a linear regression. You can also have a polynomial regression, where you will be fitting these examples to a polynomial function, which is a quadratic function, or something like y is equal to ax square plus bx plus c. Now we are having a quadratic polynomial. So y is actually equal to, say, ax square plus the bx plus c. Here the function is a quadratic function, and basically the quadratic function will be having a different shape. So like that, you can have any order polynomial, so that you can get the basic fitting function, so that you can predict what will be the value of y when you know the value of fx. Fx is the function. So this function approximation is generally known as a linear regression. So linear regression can be actually used to find out or predict what will be the value of y for a given x, where you don't know what is the value of y. But if you can approximate a function y is equal to fx like that, you can find out what is y. So an example is given over here. This is basically the energy observed and energy predicted. So basically, if you are using that, if the prediction is correct, what you will be getting is it's a line like 45-degree line. But basically the predictions are a little bit different, say a little bit from this line. That means that much error is there in this observation. So basically linear regression problems, basically it approximates the given distribution or the fit or the given distribution. It is fitted to a line, and you will be finding out the slope of the line, and you will be finding out the intercept of the line by the y-intercept, so that for any value of x, you can find out mx plus c that is actually equal to y. So this is basically the crux of the problem. In polynomial regression, you will be fitting, basically you will be fitting the examples using a polynomial function, so that y will be something like a polynomial, a higher degree polynomial, like something like a second order polynomial like x square plus bx plus c. Here y is depending upon the square of x, square of x, and as well as some constant. So basically any polynomial you can find out, and this is basically an optimization problem where you'll be finding out the value of the coefficients a, b, and c. So it is what is known as a polynomial regression. Polynomial regression also, it's a method of regression for somewhat complicated distributions and fitting that data points to a polynomial function. So I think I will stop the discussion on regression there. Now, another important algorithm which is used in machine learning is the support vector machine algorithm. So support vector machine is it is basically known as an out-of-the-box algorithm, and it is basically always basically if you just do a neural network analysis or something like a neural network for classification and all, generally the solution what we are going to get is something like not an optimal solution or suboptimal solutions, and also the convergence to solutions are also not guaranteed. But since support vector machine, the basics of support vector machines are clearly based on quadratic optimization. Whatever we are getting is an optimized output. That is, we are getting an optimal solution for the support vector machine. Support vector machine also, it is a supervised learning algorithm that can also be used for classification. Primarily, it can be used for classification. It can also be used for regression. It can be also used for pattern matching. So many things. However, it's primarily used for classification problems. The goal of support vector machine is to create a hyperplane or a decision boundary that can segregate data set into different classes. Fundamentally speaking, the basic support vector machine is a binary classifier where it will classify positive and negative classes. We have two classes. We want to learn a decision boundary which will be having a maximum margin. So support vector machine basically looks for a decision surface or a decision surface. Here the decision surface between two classes. Say suppose we consider two classes. All these examples belong to the class 2, and these examples belong to class class 1. Say class 1. And what we want is we want a decision surface. This is the decision surface. This is the decision surface. So this is the decision surface. What is the equation of the decision surface? Decision surface for this particular two-dimensional problem. For a two-dimensional problem, the decision surface is a line. And if it is a 3-dimension, the decision surface is a plane. And if the dimensions are very high, the decision surface is a hyperplane. So in order to demonstrate the simplest case, we'll consider that data is distributed. Data is having a two-dimensional data. So we have two classes of data. The dimensions are 2, and the dimensions are 2. And in that case, we have one feature here and one feature here. The total dimensionality of the data is 2. So the decision surface will be in the form of a line. As we know, what is the equation of the line? Line is equal to I is equal to mx plus c, or we can also say that it is equal to w transpose x plus b, that is equal to 0. This is mx plus c format. So w transpose x plus b is equal to 0 is the equation of this optimal decision surface. So basically, support vector machine tries to find out this decision surface, and this decision surface is having a very important property. This decision surface is known as the maximum margin decision surface. Maximum margin decision surface means actually this is the original decision surface. This point, this one. This is the original decision surface, and you can also see two marginal hyperplanes like the dotted lines over here. I hope you are seeing the dotted lines. So these dotted lines are known as the marginal hyperplane. The perpendicular distance between the marginal hyperplane is known as the margin. The margin is actually known as the distance between the marginal hyperplane. And how do you draw the marginal hyperplane? The marginal hyperplane is actually drawn through the examples of one side it will be in this class, another side it will be the other class, and these marginal hyperplanes are drawn through the examples which are closest to the hyperplane. Here it is only one example is there. Sometimes there can be another example here also. So these marginal hyperplanes are drawn in such a way that it is passing through the closest examples from these classes. This is the class 1, and also you can see this marginal hyperplane passes through this example. That is, this example is actually belong to class 2. So, and basically the distance between the marginal hyperplane is known as the margin. And what you are going to find out is you are going to find out the optimal decision surface given by W transpose X plus B, where W is known as the weight vector and B is known as the bias. Basically, they are equivalent to W transpose X is something like mx plus c for a line. So in higher order, it will be different cases. So basically, it is known as the weight vector. X is actually your feature vector. W is known as the weight vector, and B is the bias. So in a two-dimensional case, it is actually equivalent to a line which is equal to mx plus c format. And this is basically the decision surface between two classes. And this decision surface is the optimal decision surface. Why? Because the decision surface is having the maximum margin. And what is margin? Margin is the perpendicular distance between the marginal hyperplane. What are the marginal hyperplane? Marginal hyperplanes are the hyperplanes that are drawn through the closest examples from one class and positive class and the negative classes. You can see that one example is on the marginal hyperplane and another example is there on the marginal hyperplane. And the examples that are on the marginal hyperplanes that are known as the support vectors. Okay. So that is why the particular algorithm is known as the support vector machine. So basically, the support vector, once you find out the support vectors, what are the support vectors? Support vectors are examples that are lying on the marginal hyperplane. Once you can get the marginal hyperplane, or once you can trace out the support vectors within the data, training data, you can also get the equation of the optimal decision surface. This is basically the strategy behind the support vector machine. So in the support vector machine, what you are going to do is you have to find out the optimal value of the weight vector W, and you have to find out the optimal value of the bias so that you can get the optimal decision surface. What is the optimal decision surface? Optimal decision surface is the decision surface that is having the maximum margin. So basically, you have an optimization problem where you will try to maximize the margin. Later on this analysis, you can find out that maximum margin corresponding to the minimal norm of the weight vector. The minimal norm of the weight vector means what? W transpose W is the norm of the weight vector. So when W transpose W becomes minimum, the margin will be maximum. So there is an inverse relationship between the norm of the weight vector and the margin sigma, margin rho, and the norm of the weight vector. There is an inverse relationship. Is proportional to inverse of these things. So you will try to minimize the norm of the weight vector, and you will try to maximize the margin of this particular decision surface. And whatever you are getting is the value of the optimal value of the weight vector W and optimal value of the bias. And once you get that, you will be getting the optimal decision surface. So this, using this optimal decision surface, you can just find out any unknown example, whether it belongs to class 1 or not. How you will find out? You will just substitute any unknown xt, that is W transpose X plus B is equal to 0 is the equation of the decision surface. Suppose you have an unknown example xt, you just substitute W transpose xt here and just evaluate this. If it is resulting a positive value, the example actually belongs to class 1. If this is evaluated to be negative, then the example belongs to this class. This is basically the classification strategy using support vector machine. So once you can get the value of W, once you can get the value of B, any unknown example xt can be classified based on the value of the function W transpose xt plus B. This is basically the strategy of the support vector machine. Any questions on support vector machine? Okay. I think we'll make the discussions on the end of the session. We'll discuss what is the name-based classification. Basically, name-based classifier is also a supervised learning algorithm. Generally, it makes use of the probabilistic and the statistical details of the data. Just like you will make use the statistical. You will estimate the statistical parameters like the mean, variance, covariance, all these things. And once you find out the mean, variance, and covariance, you can also find out, and if you assume that the data is basically distributed as per the normal distribution or the Gaussian, the distribution of the data is Gaussian, you can find out the basically the probabilities. That is, you can find out the posterior probability, which is equal to likelihood into prior divided by evidence. So if you know the likelihood probability, you can also find out what is the likelihood probability if the data is distributed as a Gaussian distribution. And when the data is distributed as a Gaussian distribution, the most important parameters are the mean, the standard deviation, and the variance and covariance. And once you can estimate different classes, the variance and covariance, and the covariance matrix, you can also find out the probability, likelihood probability, that is P of P given A. You can also have the prior probability P of A or P of B, and also you can also find out an evidence factor, which is basically a normalization thing. So what you are going to get is basically modeling the data as a statistical model and extracting or estimating the statistical parameters like mean, variance, covariance, standard deviations. We can model this data based on the standard normal distribution. We'll assume the data distributed as a normal distribution or a Gaussian distribution. And if you assume the data to be normal or Gaussian distribution, we can also identify we can also find out the probabilities P of X given C, or basically P of X given P of A given B means it is basically an unknown example P of X, say the posterior probability P of X given C1. This is basically the posterior probability that the data X, an unknown data point X, belong to the class C1. We can also get the probability P of X, a particular data point X, that belongs to C2. Like that, we can also find out the probability that P of X given Cm, where M is the total number of classes. Suppose you have M number of classes, you can find out what is the posterior probability that the X belong to the class C1. What is the posterior probability that X belong to class C2? What is the probability that X may belong to class Cm? And if you are able to find out the probability, posterior probability, and how do you find out the posterior probability? By estimating the likelihood probability, which can be estimated from the data. You can estimate the likelihood probability. You already know the prior probability of the data, and also you will be having the evidence factor, which is actually the normalization factor. And from that you can find out P of X given C1, the probability, the posterior probability that X may belong to class 1, P of X given C2. This is the posterior probability that data X may belong to class C2. And out of this, we will be getting a highest probability. Say this is getting 0.9, and altogether the other things, other probabilities are something like like that. You are getting some probabilities, and this is coming out to be the maximum. In that case, what we can say that the posterior probability of X belong to C2 is the highest probability. Then there is a very good chance that X is belonging to C2. So this is basically the classification using the naive-Bayes classification. So in the case of naive-Bayes classifier, there is also an assumption that data is highly decorrelated. That is, there is no correlation between the individual features of the data. All the features are highly decorrelated. In that case, the covariant matrix for this data set will be having only the diagonal elements, and all other off-diagonal elements, that is covariance term, will be 0. So you will assume, actually this is an assumption only, you are assuming that in the naive-Bayes classifier, the covariance matrix will be an identity matrix, it will be a diagonal matrix, and all the diagonal elements are the same. That means the variance, basically sigma square, is uniform. That is, it is constant, and it is applicable to all classes. That is what is the naive-Bayes classifier. You can also have other conditions, like you can take the full covariance matrix. You can also consider the covariance matrix is of a particular shape. So all these cases are possible, but the most simplest method of this Bayesian classifier is the naive-Bayes classifier, where you are assuming that the data is actually basically highly decorrelated. It is all these features of this data are independent. The algorithm is called naive-Bayes, as it Bayes' naive theorem. It follows that says that variables are independent of each other. That is, all these features, what are the variables associated with the data, that means the features associated with an example, they are highly decorrelated. There is no correlation, or the covariance matrix is, or the other way we say that the covariance matrix is an identity matrix where only you will be having only the diagonal elements, and all these diagonal elements will be most probably the same. So this is what is the probability. So basically you will be estimating the statistical variables, like you are assuming the data distribution to be Gaussian or normal, and since the normal distribution or the Gaussian distribution, the most important parameters that are associated with the Gaussian distributions are the mean, variance, covariance, and you will estimate these variance, covariance for each classes, and based on that you may find out what is the likelihood probability, and also you will be knowing the prior probability. From that you can calculate the posterior probability, and once you get the posterior probability, you can also find out what is the posterior probability of P of X given C1, P of X given C2, so and so, and whichever is having the highest posterior probability, X will be associated to that class. So this is the way how a classification task is performed using naive-Bayes classifier. In the case of naive-Bayes classifier, the most important aspect is we are assuming that data is highly decorrelated. That is, there is no covariance term exists in the covariance matrix. That is, the covariance matrix is in the shape of an identity matrix, where all the shape of an identity matrix, or it is a diagonal matrix where all the diagonal elements are the same. That is what is the naive-Bayes classifier. K nearest neighbor algorithm is a very, very popular and very easy algorithm to implement. The K nearest algorithm is a supervised, again, it is a supervised learning algorithm that can be used for classification, regression, and so on. So this algorithm works by assuming the similarities between, basically it is a distance-based, we can call K nearest neighbor as a distance-based algorithm, because distances are basically very important thing, metrics that can be used in many different algorithms, because all these algorithms are generally distance-based algorithms. In the K nearest neighbor algorithm, I will just demonstrate like this. It is something like we will consider, say, some distance. There can be many distances like Euclidean distance, Mahalanobis distance, Manhattan distance, cosine similarity measures, like Minkowski distance, Manhattan distance, all these distances. So basically, distance-based algorithm generally use Euclidean distance, Minkowski distance, Manhattan distance, Hamming distance, or so many other distance measures are available for computing the distance between two vectors. So K nearest algorithm is a supervised learning algorithm that can be used for both classification and regression problems. The algorithm works by assuming the similarities between new data point and available data points. Based on these similarities, the new data points are put in the most similar categories. It is also known as the lazy learners. It's also known as a lazy learner algorithm. I will explain why it is known as a lazy learner algorithm. Lazy. Why it is known as a lazy learner. So the general arrangement for K nearest neighbor algorithm will be like this. I will show a two-class problem where we can say that a category B, class B examples are actually shown by category B examples, or class 2 are examples are shown by diamonds, blue diamonds, and the green diamonds are actually category A. There are two classes, and of course we have an unknown example here. This example is an unknown example. Okay. This example is an unknown example. Okay, this particular example is a test example or an unknown example. We will find out the K neighborhood. K neighborhood means here K will be a positive integer. Most probably it will be, K will be considered as an odd number. Say for example, my K is, here I have taken K as 1, 2, 3, 4, 5. K value is taken as the 5. So 5 neighborhood. What I am taking is, I will consider 5 neighbors of, so this particular red circle is the neighborhood. In that neighborhood, how this neighborhood is found out? This neighborhood is found out by considering or finding out 5 neighbors of this particular example. The closest examples, 5 examples we will consider, and we are creating a border or fence like this fence, and basically this fence is formed using some distance measures like Euclidean distance or something like that. So in a 5 neighborhood, K is equal to 5. In a 5 nearest neighborhood, how many examples are there? Except this, the test example or unknown example, these 2 examples actually belong to category B, and these 3 examples belong to category A. So the majority of the nearest K nearest neighbors, K means 5, the majority of the K nearest neighbors are belonging to the category A, that is these green diamonds. So the algorithm will say that the unknown orange example, this example, there is a very good possibility that this particular unknown entity may belong to category A. This is the way the K nearest neighbor algorithm functions. And basically, the K nearest algorithm, finally we need a test example. We have to find out all the distances. We want to find out the distance between all examples, category A and category B, and then we'll arrange the distance into some increasing order, and then we'll assume what is the value of K, and based on the K, suppose K is 5, we'll take the top 5 elements from the list, and out of that top 5 elements, majority belong to which class? If majority belong to category A in this case, then this unknown example is also belonging to category A, and we can increase the value of K. So the problem for this K nearest neighbor is, if you take K is equal to 5, you are getting a result like this. Sometimes if you get K is equal to 7 or something like that, probably the results may be changed. So how to find out the optimal value of the K? That is also so basically the model parameter is K. So the assumption of the K is very important thing. So depending upon the value of K, the results may prompt to change. So basically, you need to have some optimal solutions for finding out the value of k. That is the problem. That is the k nearest neighbor problem. K nearest neighbor problem is a very straightforward algorithm. The implementation is very simple. Only thing is that it is a distance-based algorithm. So you have to find out which distance is more suitable for this. So in this case, the Euclidean distance is being considered. You can also consider, say, other distances like Bhattacharya distance or any other distance, city block distance, Minkowski distance, or Mahalanobis distance. Any type of distance measures can be considered for measuring the distance between an unknown example and to all the training examples. Once the distance is being computed, the examples are being arranged in increasing order of the distance, and the top examples are k examples are taken, and you will find out the top out of this top k examples, majority belong to which class. Then we will find out that class and associate the unknown example to that class. This is basically known as the k nearest neighbor algorithm, which is considered to be the simplest algorithm for classification, and most of the time it is working very hard, very properly. Now I am coming to the basic observation that why it is known as a lazy learning algorithm. The k nearest neighbor algorithm is known as a lazy algorithm. There is an opposite algorithm, is the greedy algorithms. So this lazy algorithm, why it is known as, because it is actually, the decision is basically based on the nearest neighbors. It is searching the solution in the nearest neighbor. It is not going to the entire data set. It will just it will just fix the solution, or it is just finding out the solution with the help of the nearest neighbors of the unknown examples. So it is very lazy to explore the entire data set. That is why the algorithm is known as a lazy learning algorithm. And lazy learning algorithm actually they actually take the examples which are on the vicinity of the given example. It is not exploring the entire data set for taking a decision. So that is why it is known as a lazy learning algorithm. There can be greedy algorithms are also there, but the value of k should be justified. That is why k value has to be taken very genuinely, and the algorithm is, most of the cases, it is a lazy learning algorithm. If you take the value of k very large, it may leave the laziness and it will go to a greedy search. But the problem will be in a greedy search. The time consumption will be more. That is, it has to find out, it has to consider all the examples and then find out who will be the nearest neighbor, who will be the majority among the nearest neighbors. Okay, now we will come to another very popular algorithm. Actually, this is an unsupervised algorithm, which is known as the k-means clustering. Clustering is actually different from the classification. Classification task is actually assigning a class label to an unknown example. Regression is actually you are finding out what will be the value. You are predicting the value of the function at a point of x, variable x, and you are predicting or fitting a function to the data set. Clustering is actually, it is an unsupervised way of doing things. It is basically clustering the given data, and the k-means clustering, the k value is actually the number of clusters, or it is basically an assumption which is being taken at the initial stages, that the underlying data contains how many different clusters. So if you assume that the underlying data can belong to two classes, then you will take k is equal to 2. K-means clustering is one of the simplest unsupervised learning algorithms, which is used to solve clustering problems. The data set are grouped into k different clusters based on similarities and dissimilarities. It means data set with the most of the commonalities remain in one cluster, and which is very less or no commonalities between the other clusters. In k-means, k refers to the numbers of clusters, and means refer to the averaging the data set in order to find out the central. Basically, that mean of the cluster. That is what is there. So basically, k-mean clustering proceeds like this. Initially, you need the value of k. So k can be, it's a very difficult problem to identify what will be the value of k. Suppose in a mixed data, in a group, in a data set, you have to find out essentially how many clusters are there. So first of all, we want to find out the distribution of the data, and to get some idea how many clusters are there in the data. Accordingly, k value has to be genuinely selected. So if you take the k value which is not the correct one, your clustering will not be having very good clusters. It will not be providing very good clusters. So basically, the problem is the model parameter here is the value of k. So you have to select the value of the k in a very genuine way. There are different algorithms are there, or different methods are there to find out the value of k, the optimal value of the k, like knee algorithm, and also Silhouette analysis. All these methods like knee algorithm, Silhouette analysis, Silhouette analysis. All these methods are basically used to find out the optimal value of the K. So basically the algorithm proceeds like this. Just like an example here, I have mentioned two categories are there in this. Actually, the initial stages, the data is actually green circles. That means the entire data belong to one group, one cluster. And now you feel that the data is basically belong to two clusters. Something like this, you can say that the data basically belong to distributed as per two clusters, something like this. This is one cluster. And suppose this is another cluster. This is another cluster. Then of course these two clusters are different, isn't it? So basically what you are doing is in the K-means, first is you will be assuming what is the value of K, or genuinely you obtain how many clusters are there. So as per my observation, it is actually having two clusters. One cluster is like this. It is also having another cluster like this. So I feel that it is having two clusters like this. Based on the assumption, I take randomly 2 points, which can be an exterior points, or even I can take 2 points among the data, this point and this point, or any random points I can take, and I can consider they are the means of these two clusters. I am assuming that data contain two clusters, and I will select some 2 points here, 1 point, one mean here, this is mu1, another mean here, that is mu2. These are, I am considering that these are the means of my clusters. And now what I will be doing is, I will consider this mean mu1, and I will consider this mean mu2, and then I will take each data point. I will find out the distance between this data point with this mean. I will also find out the distance between this data point with this mean. So I will be getting distance 1, and I will be getting distance 2. So based on the distance, and I can find out which distance is the minimum. That is, if distance D1 is minimum, then I will categorize, I will just put the data into this cluster, mu1 cluster. So this point is put into this cluster. Next, I will take another point. I will compute the distance between this point and the mean mu1, and I will take the distance. I will compute the distance between this point and the mean mu2. And based on the distance, whichever is the smaller distance, I will put the particular point into another cluster. And at the end of one epoch means if I go through all the data points, finally what I will be getting is I will put all the points in either in this cluster or this cluster. So at first epoch or first round of experiments, all the data points are divided into two clusters. So basically, this may be the clusters. So at the end of the day, what I am getting is one cluster I am getting like this, and another cluster I am getting like this. So this is the two clusters in the first round I got, and this is actually with this mean, this is the mean points. Okay, now I got two clusters like this, and then what I will be doing is I will recalculate the mean. I will recalculate the mean now. So these two clusters are obtained, and this is the decision boundary between these two clusters. And now I will recalculate the mean. So the mean will be shifting from this point. This is this point. Mean will be shifting from this point to a new mean. So this is actually the new mean. So I have the mean, new mean, mu1 dash. I have the new mean, mu2 dash. So these two new means are obtained. So here the mean is shifting from here to a new mean is obtained. So this is mu1 dash, and this is mu1 dash, and this is mu2 dash. Now I will do the entire process once again. I will take each example. I will consider this point. I will find out the distance between this point and the mu dash. I will find out the distance between this point and the mu2 dash. Based on that, whichever is the minimum distance, I will put that particular example into that group. And this process will go for the entire example. Again, at the end of the day, I will be getting a different clusters. Say something like I will be getting a cluster like this, and I will be getting another cluster like this. Okay, another cluster like this. Okay, I will be getting another cluster like this. Okay, so now the new decision surface is like this. Of course, these decision line differentiate between this cluster and this cluster. The process will complete. The process will repeat. And now I can recalculate the mean. So the mean will be somewhere here. So the new mean will be obtained. So mean will be shifting from here. A new mean will be coming like this. The mean will be shifting here. So at the end of the day, after this process, I will compute the mu1 double dash, mu2 double dash. The process again will repeat. So this process will goes on till at what point we will stop. The algorithm will stop when there is no further change in the mean. That is, the process goes for some 100 rounds or 1000 rounds. Finally, there will not be any further change in the cluster. That is, all the data points will be again coming to the same clusters. At that point, changes in the mean will be minimal or very small, or it will be equal to 0. So that will be the termination criterion for this K-mean clustering. So once there is no change in the mean, I will stop the iterations. At that point, whatever it is resulting, you are getting two distinct clusters. These are the two clusters which is formed at the end of the day. So without any labeled information, this is clustering the entire data point into two groups, or two classes, or two categories, or two clusters. So cluster number one, and cluster 2. So this is actually without having any information about the level of these examples. We started with some k. We considered k is equal to 2. We got two clusters. Suppose you take k is equal to 3. Probably you might have got 3, where the error may be more. So this is basically the k-means clustering, and as we know that k-mean clustering is basically one of the unsupervised algorithms which are very popular. The last one I am going to discuss. Is another well-known algorithm which is known as the principal component analysis. So far we have discussed classification, regression, clustering, and all. These are all pattern analysis tasks. Classification is a task, pattern analysis task or machine learning task. Clustering is a machine learning task. All these are machine learning tasks. Principal component analysis is another task which is actually used for dimensionality reduction techniques. This is basically when the dimension of the data increases. For example, say the dimensionality means, suppose you have a problem like adult and child classification. This is an adult and this is a child. So adult and child, what you require is say you need some measurements. You need some measurements that can be taken from the adult. Say for example, we are taking the weight and the height are the two parameters or the features we consider for this problem. So height, suppose you have a person who is having the height 170 centimeter and who is having the weight is equal to 80 kg. Probably this weight is above 80 kg and height is above 170 centimeters. Probably this person will be an adult. Suppose you got another reading, weight is equal to 20 kg and height is equal to 60 centimeter. Probably this may belong to a child. So of course, what we can do is we can classify an incoming person based on its height and weight. If weight and heights are basically very high, then the person may belong to adult class. If the height and weights are actually belonging to the lower left corner, that means lower weight and lower height, the person may belong to a child. This is a basic argument. So height and weights are considered to be the features. And for this particular problem, the number of features are height, one feature, weight, one feature. So the dimensionality of the data is 2. That means height is one feature, weight is another second feature. So the dimensionality is 2. But most of the pattern machine learning tasks or pattern analysis tasks, the dimensionality of the data will be very huge. You may extract a lot of parameters. If you take the DFT or FFT of a particular matrix and all, you may get a matrix which will be an n cross n where n is equal to thousands or 10,000. So the number of features you are extracting from data, say for example, images or audio, you may extract huge amount of features. Generally, all these features may not be very useful in your application. So what we have to do is, because when the number of features increases, what happens is the system will become very complex. The model is becoming very complex. When the model complexity increases, the computational cost and everything will increase. So generally in machine learning applications, probably a dimensionality reduction technique will be used. The most commonly used dimensionality reduction technique is known as the principal component analysis. The basic idea behind principal component analysis is something like you are having the original data. The data will be a d-dimensional data. So what you are doing is the original data is d. For example, you have an image and you are extracting gist features from the image. The original D is something like a 512 dimension. So basically 512 dimension is a very huge dimension, and original data example will be a point in a 512 dimensional Euclidean space that we can say. So 512 dimension is a huge dimension, and it will be making the system very complex. You have to address 512 features, you have to process it and all those things. So instead, if you can reduce it, the dimensionality to some say 100 or say some 80, the dimensionality reduces, say 100 or 80, it will be a better representation. But in that case, you should not lose any discriminatory nature of the data. So principal component analysis, what you are doing is, in an original dimensionality D, what you are going to do is, you are trying to project the data onto another direction, another dimension L, which is generally very much less than that of D. Say for example, if D is 512, L may be 100 or 80. So you are projecting the original data into a lower dimensional space. So that is what is done with the help of a PC. And how this is done? This is done with the help of finding out an eigenanalysis on the covariance matrix of the data. Suppose the data is 512 dimension. The covariance matrix sigma will be a D cross D matrix. D cross D matrix. This D is 512 into 512. So what you will be doing is, you will be subtracting the entire mean of the data from this cover, the data. The data set is actually centered to the origin. This is known as a whitening transform. You will be reducing, subtracting the mean from the data, and the mean reduced data, you will find out the covariance matrix. The covariance matrix of the data will be a D cross D matrix, and you will conduct an eigen analysis on the covariance matrix. If you do an eigen analysis on the covariance matrix, what you are going to get is an eigenvector matrix and an eigenvalue matrix. So this eigenvector matrix is again a D cross D matrix, and the eigenvalue matrix is actually a D cross D matrix. Only thing is, it is a diagonal matrix with only a diagonal elements are there. There will be D diagonal elements. So these eigenvalue matrix, this is the eigenvalue matrix, and this is the eigenvector matrix. What you are going to do is, what you will be doing is, you will be finding out the significant eigenvectors based on the eigenvalues. We can see that most of the eigenvalues, these D number of eigenvalues, and most of these eigenvalues will be insignificant. Only you will be getting a very few eigenvalues are significant. So what you will be doing is, you will consider only those eigenvalues, and you will find out the corresponding eigenvectors. So suppose you have only L eigenvalues are significant, all the L plus D eigenvalues are insignificant. That is, from eigenvalues from 1 to L only you will consider. L will be 100, D will be say 512 in our example. So all the 101 to 512 the eigenvalues are discarded, and the eigenvectors corresponding to L number of eigenvalues are taken, and you will be projecting the original data, which is actually in a D dimension. You will be projecting onto the eigenvector directions, which are only L eigenvector directions. So what you are getting is, we are getting a projection of the original data into L significant eigenvector directions. This is a more popular or more compact representation of the original data without losing much of its information. So this method is functioning very, very nicely in most of the machine learning tasks, where the original data of very high dimension, say D, can be reduced, dimensionality reduced to an L dimension, where L is very much less than that of D. So this is the practical idea. So the steps which are used in principal component analysis, you will just reduce, subtract the mean from the original data. Then you will find out the covariance matrix of the original data. You will do an eigen analysis on the covariance matrix. And by doing the eigen analysis, what you will be getting is an eigenvector matrix. You will be getting an eigenvalue matrix. You will find out, you will sort actually the eigenvalue matrix as an order of significant value, that is the largest value to smallest values. Accordingly, you will sort the eigenvectors also. And then you will consider the top L eigenvectors, where L is a very small number compared to D. And you will project the original data, which is already there in the D dimensional projection, which is actually projected onto a lesser number of directions, which are actually the directions of the most significant eigenvector directions. So which are L only, L is very much less than T. So you are getting a lower dimensional projection of the original data, where each eigenvector directions are orthogonal and independent directions. That is, data is being represented in independent directions and mutually orthogonal directions, because eigenvectors are there mutually orthogonal. So we are getting a most independent directions or basis vector directions. We are projecting the original data. This is basically what is known as the principal component analysis. This is basically known as the principal component analysis. So these are the algorithms which I am going to explain in this session. So finally, I'm stopping here because time is almost reaching 9, and I'm stopping here. If you have any doubt, you can also ask. So I think time is already, I extended my time. So here I'm stopping my presentation. Thank you.
Thank you, sir. Now it's time for you to ask if you have any doubts regarding any of the topics. You can either unmute your mic and ask your question, or put the question in the chat box.
So I have a doubt.
Yes, proceed.
So when we do all these machine learning algorithms, should we go for this dimensionality reduction?
Yes. Basically, what happens means, as the dimensionality, generally it will be very huge, because when you take video as the input, or audio as the input, or images as the input, when you extract features, you may grab a lot of features for the meaningful representation. But generally, all these features, something will be redundant, something will be duplicate, something will not be very much useful, something will not be conveying much information. Such things has to be identified. So principal component analysis is one of the methods by which we can remove insignificant information in the data. So it is basically used in many algorithms where initially you will do a dimensionality reduction either with the help of PCA, or many other methods are also there, like Fisher discriminant analysis, generalized discriminant analysis, like many methods are, and kernel based methods are also there. So it is always better because your model will be very light, simple, because your data, basically what happens means, suppose you take the data with 512 dimension. Suppose you want to find out the Euclidean distance between two data points. Basically the computation is 512 computations are there, isn't it? But if you reduce that to say 200, 100 or something like that, number of addition, multiplication, all these things will be reduced. So that the computational complexity will be greatly reduced.
Thank you, sir.
Thank you. I hope no further discussions. So students from Government Engineering College, they can come and ask any doubts personally also, because we'll be there in the college. Other people, you can ask any of your clarification regarding the actual implementation and all. You can just ask in email, send an email. My email is actually smohan. I'm just writing here, smohan@geckkd.ac.in. If you have any clarifications or any doubt or anything regarding your projects work or something like that, smohan@geckkd.ac.in. You can just drop in a mail, and then if time permits, I will reply to you. So once again, thank you for patient listening. I think time has been extended so much. So good night and
Sir,
best
there is
wishes
a
to all.
question raised in the chat box. Can
Yes,
you
can you read it?
Can you explain how hyperplane is chosen in non-linear case in SVM?
Yeah, basically, so far I have explained. I will just go to that slide. So this is the slide which is corresponding to that hyperplane. This is the hyperplane. So here the hyperplane is it's basically a line that means linear, isn't it? So generally in non-linear this thing, you cannot draw a hyperplane exactly which is completely classifying these two classes separately. So there may be some examples. So in that case, what happens means data is not linearly. That case we'll say that data is not linearly separable. Okay. In that case, I think that diagram, the projected thing is not coming. It's moving. Whether you are getting a movement in that slides, I think something is there. I will just once again stop sharing, then I will share it again. Just one second. I will just share one second. Okay. I hope it is. I think that screen. What screen you are getting a movement in the screen or? Okay. Anyhow, the screen is actually not required in that case. So in the original figure which I have shown is data can be separated using a line or a hyperplane or a plane or a hyperplane. But when the data set is non-linearly separable, some examples may even cross into the marginal space, or some examples will be even in the on the other side of the marginal hyperplane or the original hyperplane. So in that case, there are two types of violation. If the data is actually inside the margin, but it is in the correct side of the hyperplane, that data actually will be a data which is actually in the marginal space, but not actually crossing over to the other space. So it may not create a misclassification. But when a data crosses that hyperplane and go to the other side of the hyperplane, it may create a violation, and that will create a misclassification. So there are two types of violations that can happen when the data is not linearly separable. So what we will be doing is, in that original problem, we will consider some slack variables which are known as the slack variable, that is penalty factors. So for each example which causes some penalty or something causes the violations, we will penalize them. So in the original optimization problem, what we'll be doing is we will just penalize, we will just consider this and we'll try to find out. So in this case, what we are going to find out is we want to find out a hyperplane with the maximum margin. That is in the original case. In addition, we want to minimize the penalties also regarding the violations. So we want to minimize the violation. We want to maximize the margin. Like that, we want to find out a hyperplane. So this hyperplane is actually allowing a little bit. That is why it is known as a soft margin hyperplane in the case of nonlinear separable patterns. In the linearly separable patterns, it is got a hard margin hyperplane, whereas here it is a soft margin. Why it is called a soft margin means it is basically allowing some violations, like a data example can be inside the margin. A data example can be even in the wrong side of the margin, wrong side of the hyperplane. So we are permitting that case for the non-linearly separable class. So basically the optimal hyperplane will be that hyperplane with maximum margin plus it is having minimal penalty values. That is the violations are to be minimized. A hyperplane that will minimize the violations. So the optimization problem will be having an additional constraint, that is the hyperplane should minimize the number of violations. That is the penalty term should be even smaller. That is basically the conditions we will be applying with the non-linearly separable classes. I hope you understood, isn't it? The original hard margin support vector machine, there is no penalty terms or slack variables. We are just going for the optimization problem that maximizes the margin. In the case of soft margin hyperplane, we allow a little bit of violations. Violation can be of two types. All these two types of violations are penalized, and we are finding out the hyperplane that will be having the maximum margin. In addition to that, which is also minimizing the number of violations. Then we will get an optimization, optimize the hyperplane. So this is the way the solution is being derived. I hope you understood.
Yes, sir. Understood. Thank you, sir.
Okay, thank you. I think other doubts, I think we will discuss offline. And thank you for patient listening. And I'm just finding up. Thank you all the organizations for giving me the opportunity to address this IEEE Malabar subsection webinar, that is bi-weekly webinar. So thank you and thanks a lot.
Thank you, sir. So on behalf of IEEE Malabar subsection and IEEE SPGEC Kozhikode, I would like to express my heartfelt thanks to everyone who attended our webinar today. I would like to extend my sincere gratitude to our esteemed speaker, Dr. Shaji Mohan BS, for sharing his expertise and knowledge with us. His presentation was enlightening and thought-provoking. We are sure that everyone who attended the webinar learned a lot. Thank you so much, sir. Once again, I would like to thank all the attendees for joining us and actively participating in the discussion. Your presence and engagement made this webinar a success. We hope that you found the session informative and valuable, and we look forward to see you again in our future webinar series. Thank you so much.
Thank you.
All the participants, you can leave the meet now.